So I thought I'd bring us out of the oceans and maybe onto land for a short while. And I wanted to say that wildfires are a major force on our planet. They're strongly impacted by environmental changes. Therefore, we might be able to suggest that periods of major global change might be able to impact fire activity. So I wanted to outline the nature and contribution of wildfires to the Triassic Jurassic and the Cretaceous-Paleogene boundaries, and ask the question, could the global changes at these times make wildfires just simply a consequence of those changes, or could wildfires be a potential cause of the mass extinctions we see at this time? So just for an overview of the Triassic Jurassic and the Cretaceous-Paleogene. So both of these two events are two of the 5 big mass extinction events. The Cretaceous tertiary boundary occurs around 65 million years ago, and the Triassic Jurassic boundary occurs around 200 million years ago. And both events appear to be linked to times of major environmental upheaval. Both, as we've heard today, are associated with large igneous provinces, so the Triassic Jurassic boundary with the Central Atlantic Magmatic Province and the formation of the Proto-Atlantic Ocean, and of course the Cretaceous-Paleogene associated with volcanism in Deccan in India. But the Cretaceous-Paleogene is also associated with an impact of an asteroid or a comet which hit the Yucatan Peninsula in Mexico. And both of these events are characterized by extinctions on the land and in the ocean. So if we want to start thinking about how these global changes might affect fire, we need to consider what the key environmental controls are on fire. And I've just outlined some of these here. So of course, probably the first thing we think about when we think about environmental changes in fire is, of course, does this work? Yes? Is that we have changes to climate and weather, particularly rainfall and droughts are well known to affect fire activity, but also changes in plants such as fuel, particularly plant type, and the fuel moisture impacts fires. On a local scale, we have slope angle, and on a global scale, atmospheric oxygen levels, which can change ignition and fire spread. So we can imagine that if we were to change any of these factors here, then we would be able to alter fire activity. So therefore, we would expect alterations to fire during periods of major global change. But changes in fires can also be agents for change themselves, and I've kind of tried to highlight this in this schematic here. So I've got my forcings, so the forcings of those changes are in red, and fire feedbacks to those changes are in blue. So for example, if we were to change climate, we could cause biome shifts and change our vegetation. These two things, coupled with climate change, could change our ignition probability, and they could also change fire regimes. But the changes in fire regimes could feed back into changes in vegetation, which would impact biogeochemical cycling, altering the carbon balance and potentially feeding back to climate change themselves. So my point here is simply to highlight that fires can be agents for change themselves. They're not just a consequence of events. So here's the overview of my talk then, is what I want to speak about. Well, what's the record and the evidence for wildfires in changes to paleo-fire regime across these two events? And ask, well, what does this mean for interpretations of the environment during these two phases of major change? So I'm going to start with the Triassic-Jurassic boundary. So our key potential fire regime change driver here is climate-driven vegetation change. And this is believed to be due to a global warming event taking place over around 100,000 years. And this is believed to have impacted plant communities. For example, in the Greenland sections, we see community species richness declining around 85% throughout the latest Triassic. And in Europe, we observe marked changes in pallinifloras across the Triassic-Jurassic as well. So this is an outline of the floral changes at a starter cloft in East Greenland. And what I've done here is I've split those two changes in plants into thinking about plant architecture. So I've divided up all the species that we see changes in into broad-leaf plants and narrow-leaf plants. The broad-leaf plants are shown in green, and the narrow-leaf plants are shown in red. And what I've got here, this is a proxy for carbon dioxide. So here's the global warming event at the Triassic-Jurassic. This there would be the Triassic-Jurassic boundary. And we can see that our Triassic ecosystems are dominated by broad-leafed plants, and our Jurassic ecosystems were dominated by narrow-leaf plants. And if we look at the record of charcoals across this event, we see that this change from a broadleaf community to a narrowleaf community causes a change in, or we see, coincident with this, a 5-fold rise in the increase of fossil charcoals in the rock record. So could this change in fuel type then really influence fire? So we decided to test this in the laboratory. We undertook some flammability experiments where we ignited a range of live fuels ranging from broad to narrow leaves, and also some litter fuels. So let's just starting with our live fuels. What we measured here, we measured how long those plant types took to ignite. And we find that our narrow-leaved species, so similar to our Jurassic plant communities, ignited much more rapidly than our broad-leaved Triassic communities. And this seems to be because they actually release their volatiles quicker when you heat those plants. So plants burn because when a fire starts to heat that plant material, it begins to break down and it releases volatile gases. And it's these gases that ignite and lead to burning of the fuel. And so we see that our narrow Jurassic leaves are releasing their volatiles quicker, causing them to ignite faster. So our live canopy fuels of the earliest Jurassic were more easily ignitable. And when we look at litter fuels, I've got two I suppose these are kind of like fire profiles. So what these are, this is time on both these bottom axes, and then we have the rate at which the fires release their heat on the y-axis. So we have ignition of our fire, then we have the burning, and then the fuel's gradually consumed and the fire burns out. And what we found was that as you increased leaf length, you tended to have a higher peak heat release rate, so the peaks in these are higher on narrow leaves. And as we increased leaf length, though, you actually saw a lower total heat release from those fires. So this suggests that our Triassic ecosystems had a higher peak heat release rate, but lower total heat release for their fires. So they were probably likely to be quick-burning, flashy fires, whereas our Jurassic ecosystems had a higher total heat release from the fires, but a lower peak heat release rate. So they had a more sustained burn. So what are our evidence for alterations to fire then across the Triassic-Jurassic boundary? Well, we can see that we seem to have two different fire regimes. Our Triassic ecosystems here seem to be experiencing generally low fire frequencies, as suggested by the lower abundance of fossil charcoals. The canopy fuels themselves were less easily ignitable, but the litter burned very quickly, although very intensely, rapidly consuming the fuel. But when we transition to the Jurassic, we have a different regime where we have a higher fire frequency. The canopy fuels burned more easily, and the litter burns for much longer duration, perhaps for a sustained period. Okay, so let's contrast that kind of regime change that we see across the Triassic-Jurassic boundary with what we see at the Cretaceous-Paleogene boundary. So our potential driver of changes to fire at the Cretaceous-Paleogene then is thermal radiation delivered by an extraterrestrial impact at Chicxulub. And this thermal radiation has been suggested to be capable of igniting wildfires. And in this case, the timescale for change is probably minutes to hours. So what is the potential for this thermal radiation to ignite and cause wildfires? So we've decided to recreate the Cretaceous-Paleogene thermal radiation in the laboratory. We've taken the most recent models of the KT impact by Joe Morgan and colleagues. And what they've done, they've created estimates of the proximal KT boundary thermal radiation through to the distal. And what they show is that the proximal thermal flux has a very high peak, but it's delivered for a very short duration. Whereas actually when you get much further from the impact, we have a lower peak, but the duration is much longer. So it's actually a higher total heat flux. So we've created these heat fluxes in the laboratory using a fire propagation apparatus, which is here. So you put your sample into the fire propagation apparatus. The scale of this sample is around 12 centimeters across by 3 centimeters deep. So this is leaf litter in this basket. And surrounding the sample, we've got 4 very high voltage halogen lamps. And we can program these lamps to ramp up the temperature and ramp down the temperature or the heat flux. So we're kind of mimicking the KT boundary by controlling these lamps. And what these images actually also show is that you see these crosses on the figure, those are what the model predictions were, whereas the solid lines are the actual recreation of that thermal flux in the laboratory. So you can see that we've managed to match those quite well. So what did we measure and observe in our experiments? The first thing we measured was, did our samples char? Did they undergo pyrolysis? And I want to point out here that charcoal can form without combustion. You don't need to ignite a sample in order to pyrolyze a sample. We also then measured whether something ignited. We looked at whether the samples underwent flaming combustion or smouldering combustion, and we observed what remained at the end of the experiments. So these are the results. And what it shows is that we attempted to ignite wood, dry wood, with bark still intact. We also attempted to ignite dry litter. So these are kind of like a worst case scenario, because obviously they're much drier than you would expect to have in a natural ecosystem. And we also tried to ignite very live but very volatile vegetation, so had a high volatile content. And what we've got this is the proximal result, this line, this is the two intermediate scenarios, and we've got two distal scenarios, and this one is the one that had the very, very long duration heat pulse. So what we see with our wood, we see that it generally only underwent very minor pyrolysis for most of the scenarios. In all of our dry litter fuels, we observed ignition and flaming combustion. But when we looked under these four scenarios with the live fuel, we only observed very, very minor pyrolysis. And in fact, some of it just literally dried out, doesn't look very different at all. But in our distal scenario, where we had a very long, drawn-out thermal pulse, we did absolutely observe pyrolysis and smouldering in our wood. Again, these two were consumed. And in our live fuels, around 50% of the samples showed flaming combustion. But what you also notice in this figure is that we have created a range of products from this. We've got some live material remaining, we've got some char and ash here, and we've got some, again, sort of wood particles, but also some charred wood. So do our results then reconcile with the Cretaceous tertiary boundary fossil record? So this plot here shows the abundance of charcoals across 8 KT boundary sites, stretching from the south, so closer to Chicxulub and up into Canada in the north. What we can see is that fires were a regular part of both the Cretaceous and tertiary ecosystems. But when we look at the Cretaceous tertiary boundary rocks, we can see that we do see some pieces of charcoal in these sediments, but generally not that much. But we did also observe a large amount of non-charred organics in the Cretaceous tertiary boundary rocks as well. So it seems that this record does seem to match what our experiments would suggest, so that's encouraging. So then what would the nature of the Cretaceous-Paleogene fires be, and what would their distribution be? So we deliberately chose to recreate either the highest heat fluxes or the longest duration pulses in the laboratory. So we really picked the worst case model predictions. There are lower predictions within the same model set, but we picked the worst case scenarios. We also took the estimates for the downrange impact direction as well, which again would have received the greater thermal flux. So the first thing we conclude is that areas outside the downrange direction would likely not have been ignited at all. But those within the downrange direction, only tinder, dead and dry fuel would have been likely ignited in proximal and intermediate distances. And I say tinder dry, so that matches our experiments of being less than 12% moisture, which is quite unnatural. Whereas live fuel perhaps could have been ignited at our distal locations, which is potentially very interesting. So my conclusion here for this part then is that the KT boundary thermal heat pulse would have likely have ignited only local fire events. And if it did, they would have been predominated by surface fires and not crown fires. So we might have been thinking maybe small local fires like this, where fuel was very, very dry. So what about the effects on plant life? Could these fires have a major effect on plant communities at the Cretaceous tertiary boundary? Well, the first thing to point out is that actually the longest heat pulse is only 6.5 minutes long. So trees are actually really well able to cope with high heat pulses. So this is a result of some experiments where people mapped bark thickness with the time to exposure of around a fire that was about 600 degrees. And we could see that only bark that's around 1 centimetre thick would actually be likely to be killed by the Cretaceous tertiary boundary pulse. But plants have amazing abilities to survive. They have underground reserves where they can regrow. They have epicormic buds hidden within their bark that allows them to reshoot as well. So we would suggest that localized fires likely had minimal impact on plant communities at this time. So we wouldn't expect thermal radiation alone to cause mass mortality in forests. So then, what was fire's power to cause change during these events? So the influence of fires on an ecosystem depends strongly on its fire regime, where fire regime includes things like the frequency of fires in an ecosystem, the fuel type, which influences the intensity of fires, as well as climate, slope angle, and seasonality. So fire regime is a sum of parts that operate together. It's not just a single thing. And it's changes in fire regime that can bring about ecosystem changes, not any of these individual things alone. So there's a relationship between fires and ecosystems that's very complex. There's a dynamic relationship where typically if you were to change the types of plants in your ecosystem like we see across these global change events, we ought to be able to change potentially fire regime, but fire regime would likely feed back into changing the types of plants that we would find. So we need to assess the linkages between global change events and their ability to change fire regime as a whole in order to understand fire feedbacks to ecosystem changes. So what about our regime changes then? So at the Triassic Jurassic boundary, we see that changes to vegetation drove a change in fire regime. We observed that there was probably enhanced fire frequency across this global change event, and there was a change also in the nature of the fires. So this suggests that at the Triassic Jurassic, we see a regime shift over the long term. But at the Cretaceous-Paleogene boundary, vegetation was simply subject to heat stress and in some cases fire. So this is a one-off fire event, and there's little or no evidence for a change in activity when comparing pre- and post-Cretaceous-Paleogene fire records. So then, to come back to my original sort of question, are these a cause, or the fires a cause or a consequence? So at the Triassic-Jurassic boundary, there's this dynamic relationship present where we've changed our fuel, which has perhaps assisted with changes to fire regime, and then this has fed back in potentially changing fuel type again. So alterations to fire could potentially be a cause of further changes at the Triassic-Jurassic boundary. So in this case, fire is both a cause and a consequence of the events at this time. But when we look at the Cretaceous-Paleogene, there's much more of a one-way relationship. We have a thermal pulse that's dried out, that's caused desiccation to our ecosystems, and in some cases fire. But the KTG impact alone can't cause floral change. So fire is very much just a consequence of this event. So in both cases then, we've got the Triassic-Jurassic boundary vegetations being a driver of change, but at the Cretaceous-Paleogene, vegetation is being very much a victim of this event. So which has the power for the greatest change? Both of these cases, fire is a consequence, but we see a shift in fire regime at the Triassic-Jurassic boundary, which could be a positive feedback on flora change. Whereas the fire at the Cretaceous-Paleogene is a single fire and a heat pulse, and this can't be a product of permanent floral change. So what does this mean? So what I wanted to sort of highlight today is that fire is complex. Fire is a consequence of changes to the Earth system, but because it can interact across a broad range of scales, it may or may not be a major direct cause of change. It can be a one-off event that may have limited direct long-term consequences, such as any fires at the Cretaceous-Paleogene boundary, or it can be a regime changing and act as a major causal agent of further change. So perhaps we should consider this at the Triassic-Jurassic boundary. So if we are to consider the role that fires have played over the ages and during these major life-changing events, then fully understanding fire's power for change is essential. Thank you.
Okay, thanks, Claire. We have time for one very quick question. We have one down here. Can we bring the microphone over, please?
Well, first I want to congratulate you for not using the word resilience. I'm thinking about the fire triad, fuel, oxygen, and ignition. Surely the vast majority of fires are ignited by lightning over the long haul, and that the frequency of lightning strikes would be influenced by other climatic factors. I wonder, is there any correlation between the atmospheric content of oxygen and the frequency of fires? Has anybody done any work on that?
Yeah, I've got quite a few papers on that as well. So yes, atmospheric oxygen strongly influences ignition. So you have, at low levels of atmospheric oxygen, up to around 17%, ignition is quite unlikely. But at 17% oxygen, you can ignite fires. And then the ignition and spread of fires rapidly increases between 19% and around 22% atmospheric oxygen. And then it continues to creep up a little bit, but then it becomes mainly to do with moisture content. So yes, atmospheric oxygen has a major effect on both ignition and spread of fires.
You didn't mention that in here, but no variation in atmospheric oxygen over these times.
So people have suggested that there was low oxygen at the Triassic Jurassic boundary, but the fact that we find actually a large amount of charcoal suggests that it probably isn't as low as some people have said. So we would have to say that atmospheric oxygen was greater than 17%. The current day is 20.9 at the Triassic Jurassic. At the Cretaceous-Paleogene, this is quite interesting. There's not necessarily a change in oxygen across this event, but oxygen is potentially higher, which is probably something you could see in those fire records. Fires are very, very common in the Cretaceous because oxygen was maybe around 25%, so quite a lot higher. Okay, thanks.
Thank you. We need some